radiation. The core's disruption connects to more tangible threats emerging beneath our feet. The changing dynamics deep within Earth are potentially altering the stability of the ground itself. The connection between core processes and Earth's surface creates a complex web of interrelated hazards that compound one another. Tectonic triggers. While radiation from a weakened magnetic field presents a serious threat, another danger lurks beneath our feet. The seemingly solid ground we stand on is actually in constant motion. Earth's crust consists of massive tectonic plates that float atop the semi-liquid mantle, moving at rates of 2 to 5 centimeters annually. This perpetual movement builds tension along fault lines where plates meet, eventually releasing as earthquakes when the stress exceeds the rock's strength. For centuries, we've understood earthquakes as purely geological phenomena, the natural consequence of plate tectonics. However, recent research reveals a more complex reality. The frequency and intensity of seismic activity may be changing due to a combination of core dynamics and climate change. These connections suggest Earth systems are more interconnected than previously recognized. A groundbreaking study published in the journal Geology has identified a direct link between climate change and earthquake frequency. The research examined regions where large glaciers have recently melted, finding that the removal of ice weight allows underlying faults to move more freely. This process, called isostatic rebound, occurs as the crust rises after being relieved of the massive weight of ice that had compressed it downward for thousands of years. Evidence comes from the Sangre de Cristo Mountains in Colorado, where researchers documented fault slip rates increasing 5-fold following glacier retreat. By examining geological markers along fault lines, they determined that these faults had remained stable while compressed by glacial ice. Once the ice melted, the pressure release allowed the faults to slip more frequently, generating increased seismic activity. Similar patterns exist in Alaska, Greenland, and parts of Antarctica experiencing rapid ice melt. This relationship between melting ice and seismic activity creates a troubling feedback loop. Climate change accelerates glacial melt, which reduces pressure on underlying faults, which increases earthquake activity. The earthquakes can then damage permafrost and ice sheets, potentially accelerating melt rates further. Earth's crust essentially groans under these shifting weights, creating a climate-tectonic feedback system that amplifies both climate impacts and geological hazards. The climate-seismic connection extends beyond melting ice. Scientists in northern Japan have discovered correlations between heavy precipitation events and earthquake swarms. Research published in Science Advances analyzed precipitation data alongside seismic records, finding that intense rainfall often preceded unusual clusters of small earthquakes by several days to weeks. Water penetrates deep into fault systems, reducing friction between rock surfaces and altering subsurface pressure. When water infiltrates fault zones, it lubricates the fault and reduces the force needed to trigger movement. This hydroseismic triggering has been observed in multiple regions worldwide where unusual precipitation patterns have occurred. These climate-triggered earthquakes have become increasingly common during precisely the same period that core changes have accelerated. The timing suggests these phenomena may be interconnected through complex Earth systems that we're only beginning to understand. The correlation highlights how multiple Earth systems can experience simultaneous perturbations that compound each other's effects. Perhaps most concerning is the emerging evidence connecting core dynamics directly to surface seismic activity. Earth's core influences our planet's rotation through complex fluid dynamics. As molten material flows within the outer core, it creates subtle shifts in mass distribution that can slightly alter Earth's rotational behavior. These changes are extremely small, measured in milliseconds of day length, but they redistribute enormous energy through the planetary system. Research from Caltech's Seismological Laboratory has identified correlations between changes in Earth's rotation rate and periods of increased global seismic activity. By analyzing decades of rotational and seismic data, researchers found that slight rotational slowing often preceded years with above-average numbers of significant earthquakes worldwide. The mechanism relates to angular momentum conservation. When Earth's rotation slows slightly, the reduced centrifugal force changes stress patterns throughout the crust. These stress changes concentrate along existing fault lines and plate boundaries. The additional stress can push already strained fault systems past their breaking points, triggering earthquakes in vulnerable regions. Core disruptions amplify these effects by adding variability to Earth's rotation. The USC study showing changes at the inner-outer core boundary suggests that flow patterns generating Earth's magnetic field are becoming more chaotic. These changing flow patterns affect mass distribution within the core, potentially creating more variable rotational effects that translate to irregular stress patterns in the crust. Evidence for these connections comes from multiple independent sources. Satellite measurements tracking variations in Earth's rotation show increasing irregularity over the past 2 decades. Simultaneously, global earthquake catalogs reveal measurable increases in both the frequency and clustering patterns of significant seismic events worldwide. The correlation between these datasets is statistically significant according to analyses published in Earth and Planetary Science Letters. We're seeing evidence of unusual seismic patterns. The New Madrid seismic zone in the central United States has shown increased activity despite being far from any plate boundary. Intraplate earthquake swarms in Oklahoma, Texas, and Ohio have increased dramatically in recent years. While some activity relates to industrial fluid injection, the broader pattern suggests fundamental changes in crustal stress distributions that align with predictions from core rotation models. The combination of climate-driven and core-influenced seismic triggers creates compounding risk. Regions experiencing glacial melt face increased earthquake probability from isostatic rebound. Areas with changing precipitation patterns face additional risk from hydroseismic triggering. Globally, shifting stress patterns from rotational irregularities add another layer of seismic potential. These mechanisms can operate simultaneously in vulnerable regions, potentially triggering earthquakes that might otherwise have remained dormant for centuries. This complex interplay between Earth systems makes earthquake prediction increasingly difficult. Traditional seismic forecasting relies on historical patterns that may no longer apply in our changing world. Disaster preparedness must now account for these new triggers, especially in regions facing multiple risk factors simultaneously. As Earth systems become more interconnected and unstable, our ability to anticipate when and where the next major earthquake might strike becomes more challenging, demanding new approaches to both science and public safety.